Okay. So today we are getting into topic 6.2 and 6.3. I just kind of combined them because they're kind of short. So make one longer lesson here. Okay, it shouldn't take too long either. It'd probably be like 20, 25 minutes or so. All right, so today we're talking about the law of conservation of energy. So this law states that in a closed, isolated system, the amount of energy will remain constant. Okay, so an isolated system is a system where the energy nor the matter can be exchanged with its surroundings. Okay, so that is an isolated system. The actual law itself is this second point here. Energy cannot be created or destroyed, only changed from one form to another. Okay, so put a big star on this slide to make sure that you know these 2 points, especially the second one in particular. Energy cannot be created or destroyed, only transformed. Okay. So the work energy theorem, this is a new concept for us today. And this is stating that to change the kinetic energy of an object, a force must be applied or exerted. Therefore, work must be done on the object to change its kinetic energy. Okay, so think of a car that is just sitting there. To move the car, you need to apply a force, which would be the gasoline burning in the engine, which turns the crankshaft, which rotates the tires, right? We need to put work into the system to change the kinetic energy of the system. So this formula here, you will find it on your formula sheet. The work is equal to the change in energy is what you will see on your formula sheet. Just know that we can find the change in kinetic energy or the change in potential energy, and that will still tell us the work that is been done on that system. Okay, so this is an important formula. Work is equal to change in energy, and that's what you will see on your formula sheet. Work is equal to change in energy. So similarly to kinetic energy, to change the potential energy of an object, we need to apply a force. So therefore, work must be done on the object to change its potential energy. So to lift a book from the ground to your desk, that is not just going to magically happen. You have to apply a force and you have to put work into it to lift that book so it's resting on your desk. So similarly to the kinetic energy from formula from last slide, so work is equal to the change in potential energy, and the change in potential energy can be found by subtracting the initial potential energy from the final potential energy. Kind of like what we did yesterday with that race car that was going down the track, right? We found the change in potential energy in that particular problem. When we're dealing with changes in potential energy, as long as the mass remains the same, we're just measuring the change in height for that. So the work done on a system is equal to the sum of the changes in the potential energy, and when you add that to the kinetic energy of the system. So we can write that as a formula like this. So this formula right here, work is equal to change in energy. That is what you will see on your formula sheet. Okay, the change in energy can also be found by adding the potential energy and the kinetic energy of the object. Okay, so these two combine to form what we call mechanical energy. We'll talk about that a little bit later on. Okay, and like what we did on the last two slides, the change in potential energy can be found by finding the potential energy of the final location or the final height, subtracting the potential energy of the initial height or location. And similarly, to find the change in kinetic energy, you can just subtract the initial kinetic energy from the final kinetic energy. Okay, so this formula will be helpful for us if we know like the initial potential energy, we know the work done, and we know these two if we're just trying to solve for the final potential energy. Okay, so you can kind of play around with these formulas to isolate what you need given the information on that particular question. Okay, mechanical energy, I kind of alluded to this on the last slide. So mechanical energy is the sum of potential and kinetic energies. So we'll just add those together, and this will tell us the total energy of a system. Okay, so this is an important slide. This will help you solve some of the practice problems on our assignment. So total energy is equal to the potential energy plus the kinetic energy. Okay. So if you're given the height of an object and the speed of the object and the mass, then you can find the total energy or the mechanical energy of a system. Okay, so I want you guys to think about this statement right here. So study the changes in energy that take place when a ball is dropped from a height of 20 meters. So at the top, at the top of it, we have maximum potential energy before we drop it. Excuse me. I'm just going to draw on here. So up here, here's our height, 20 meters. If the ball is up here, we're going to have max EP, so max potential energy, and minimum kinetic energy. So at the beginning, before it's even dropped, it will have zero kinetic energy because it's not moving. All of that energy will be in the form of potential energy. As soon as you drop it, that potential energy is being converted to kinetic energy. So the object will increase its speed the longer that it falls until it reaches terminal velocity. So when an object is, just kind of summarize what we just said. So when an object is dropped, the potential energy of the object is decreasing. This energy is not destroyed, but it is just transferred or changed into another form. So it gains kinetic energy because the ball's speed is increasing as it falls. That potential energy is being converted to kinetic energy. Okay. As that potential energy is converted to kinetic energy, all of that energy is going to be conserved. So we're just going to neglect the force of friction here. Okay. But yeah, so remember the law of conservation of mass. Energy cannot be created or destroyed, just transferred from one form to another. So in this question, that potential energy is being converted into kinetic energy. Okay, so same thing, take a second to consider this statement. So a ball is thrown into the air and reaches a maximum height of 20 meters. So we are throwing the ball up. Eventually, when it gets to the very top, its velocity will be 0 for one particular instant. Remember, we talked about this in our kinematics unit. So at the bottom here, right as we throw it, it is going to have maximum kinetic energy and minimum potential energy, right? Because it's at the lowest part of its flight. So because it's at the lowest it is, it's going to have minimum potential energy. Okay, and then when we get to the top here, all of that kinetic energy is being converted to potential energy. So at the top, when that ball is motionless, it's going to have minimum kinetic energy. And hopefully you guys will see this, it will have max potential energy because it is at the highest point of its flight. Okay. So I found my mouse, there it is. Okay, so just kind of summarize what we just said. When an object is thrown into the air, the speed decreases, so it's losing kinetic energy. It's gaining height, so it's increasing its potential energy. That kinetic energy is being converted to potential energy. And again, the total amount of energy in this system is remaining constant. So in general, whenever an object is changing its height, you can use this formula to study the changes in kinetic and potential energies. So remember, the amount of energy in a system is going to remain the same. So from a couple slides ago, we discussed the formula E total, or mechanical energy, is equal to the potential energy plus the kinetic energy. So if we know the potential energy on one side and the kinetic energy on one side and the kinetic energy on the other side, we could potentially solve for this potential energy there, okay? So kind of like what we've been doing in Unit C, we're just going to continue with substituting in our formulas. So just make sure you guys know that we use this particular formula whenever an object is changing its height. Okay. All right. So that is it for the content. So let's go ahead and get into some of the calculations. Okay, so same as yesterday, there are two screens of me. One is my face now, and one is going to be the practice problems. So please go ahead and pin the page where we are doing the examples on, okay? Oops. Okay, there we are. Okay, so here we go. So a block is being moved up a frictionless inclined plane by a force that is parallel to the plane. So remember, to be able to find the work done on a system, you needed to find the force that was parallel to the displacement of the object. Okay, so in this case, the force is parallel to the displacement, so that is going to make our lives a little bit easier. Okay, so at the foot of the incline, so I'm just going to draw a image here just to kind of help us get an idea of what's going on. So here's our block at the bottom. It has a velocity of 1 meter per second. At the top of the incline, 0.850 meters above the lower end. So here's our height. Once we push this block up the incline, we're changing the velocity. So up here, the velocity is equal to 4 meters per second. Okay, we know the mass of the block is 1.20 kilogram. And we are asking what is the work done on the block as it moves up the incline. Okay, so on our formula sheets, we will find that work done is equal to the change in energy Okay, and we need to expand this. So change in energy is equal to the change in kinetic energy plus the change in potential energy. So we can substitute in these formulas for what we've seen before. So the change in kinetic energy is EK2. So the kinetic energy of the second point minus the kinetic energy of the initial point plus the change in potential energy is going to be mg times the change in height. Okay. So we will continue to expand this. So EK2, so it'll be 1 over 2 mv2. So I'm just saying that is at our second velocity squared minus 1 over 2 mv1 squared plus, and that's just going to stay the same, mg delta h. Okay, you might notice that we have 1 over 2m, which is common in both of these, so we can factor that out. So it'll just save us some time easier, or a little bit later. So I'm gonna put a big bracket there, and then we'll have 1 over 2m, because that's what's common in both terms. Now we will get v2 squared, so our final velocity squared, minus our initial velocity squared. And then we're still going to add mg change in height there. All right. So now that we're at this point here, we can just substitute in our values. So we will get the change in energy is equal to 1 over 2. Our mass is 1.2 kilograms. Multiplied by our final velocity, so it's 4 meters per second squared, minus our initial velocity, 1 meters per second squared. Close off that big bracket, plus the change in potential energy. So our mass is 1.2 kilograms. G is 9.81 meters per second squared. And our change in height, we are going 0.85 meters above the lower end. So our change in height is, we're gaining height, so that's going to be a positive value. Okay, so this is what our term looks like. And if we enter that into our calculator, we will get a change in energy of 19.0 joules. And if we jump back to the top here, we know that work done is equal to the change in energy. Change in energy is 19 joules, so therefore the work is equal to 19.0 joules. Make sense? All good? Got a thumbs up from Stewie. Excellent. Are there any questions there, guys? No? All right. Let's continue. We only have 3 practice problems today, so we only have 2 to go, including this one. All right. So a cannonball is fired from Earth's surface. At its trajectory, it has a horizontal speed of 160 meters per second and is a height of 1.20 times 10 to the 3 meters above the ground. With reference to the ground, what is the mechanical energy of the cannonball at the highest point on its trajectory if the mass of the cannonball is 5.20 kilograms. Okay, so it is asking what is the mechanical energy. So remember, mechanical energy also equals total energy. Okay, and if we're finding the total energy in a system, we are going to find the total potential energy plus the kinetic energy. Okay, so I'm just going to draw a diagram here again. So we shot it up here. It has a velocity of 160 meters per second. Its height is 1.20 times 10 to the 3 meters above the ground. And we know that the mass is 5.20 kilograms. Okay, so let's expand these formulas here. So mechanical energy is equal to potential energy, which is mass times gravity times height, plus the kinetic energy, which is 1/2 mv squared. Okay, so now we can just substitute our values in. Mass is 5.2 kilograms. Gravity is 9.81 meters per second squared. The height of the cannonball is 1.20 times 10 to the 3 meters. I'm running out of space here, so I'm just gonna add down here. So plus, we have 1/2 multiplied by the mass is 5.2 kilograms. And we're gonna multiply that by the velocity squared. So 160 meters per second squared. So if we punch this into our calculator, we should get a value with correct sigdigs of 1.28 times 10 to the 5 joules. Any questions there? We're doing all right? Okay, rock on. Last practice problem for the day. We're going on a frictionless roller coaster. So on Thursday, after we finished the quiz, we watched the Magic School Bus where they didn't have any friction when they're on like the baseball stadium. They're just sliding around everywhere. They were big fans of friction by the end of that episode. Okay, so a frictionless roller coaster, that would be wild. It has a mass of 800 kilograms. At one point on its journey, it has a speed of 4 meters per second. And then later its speed is measured to be 20 meters per second. So VI is 4 meters per second. Our VF or our V2, whatever you guys would prefer, is 20 meters per second. We know the mass, we know the velocity, we know the height. So we know at our first velocity, so V1, the height is 35 meters above the ground. So H1 is 35 meters. Cool. So part A, there we go. So part A, we're asked to find the total initial energy relative to the ground before it increases speed. So we are concerned with our H1 and our V1. Okay, so remember the total initial energy or the total energy is our mechanical energy. And as we said last question, mechanical energy is equal to total energy. Okay, so those are kind of just synonyms for one another. So mechanical energy is equal to the potential energy plus the kinetic energy. So mechanical energy is equal to mgh plus 1 over 2 mv squared. We know m, we know h, and we know v, so we can just substitute those in. So mass, 800 kilograms, g, 9.81 meters per second squared. Our height at point 1 is 35 meters, plus 1 over 2 multiplied by the mass, multiplied by the velocity, the initial velocity, so 4 meters per second, and that is squared, mv squared. Okay, so just substitute this into your calculator or punch it into your calculator, and with significant digits, we should get an answer of 2.81 times 10 to the 5 joules. Okay. All Gucci? Cool. Okay, last question. What is the gravitational potential energy in the second instance? Okay, so in the second position, we do not know the potential energy nor the height. So we're looking for the gravitational potential energy. So this question here, so we just found the total initial energy. So we could also say E total. Remember, total energy is equal to the mechanical energy. And another thing that we have to connect from our theory side here is that just remember the law of conservation of energy, right? Energy cannot be created nor destroyed, just transformed from one to another. So the total amount of energy in that system is going to remain the same. So we know from last question that the mechanical energy or the total energy is equal to, so 2.81 times 10 to the 5 joules, but because we don't want to use our intermediates here, I'm going to write down the calculated value. So we'll have 281,080 joules as our mechanical energy or our total energy. And remember, mechanical energy or total energy is equal to the potential energy plus the kinetic energy. And in this case, we're looking at the second point. So I'm just going to put little 2 subscripts there, just so I'm being neat with my calculations. Okay, so we are isolating for this. So let's subtract kinetic energy from both sides. We'll be left with potential energy at point 2 is equal to the mechanical energy minus the kinetic energy at point 2. So EP2 is equal to mechanical energy minus EK2. So it's 1 over 2 mv, and that's at point 2 squared. We know our V2 is 20 meters per second. So we'll substitute into that, and the mass has not changed. So EP2 is equal to our mechanical energy, so 281,000 and 80 joules minus 1 over 2 times the mass of 800 kilograms times the velocity at point 2, which is 20 meters per second, squared. And if we will punch that into our calculator, we will get a potential energy at point 2 of 1.21 times 10 to the 5 joules. Okay, so if there are no questions, or are there any questions for any of the problems that we went over today? No? Perfect. Okay, I'm going to end the recording.